Okay, we can, I think, get started. We have a full quorum. I'm gonna share my screen. There we go. Let me know when you guys are ready. Maybe I open up.
Yeah, I'm good to start whenever. Sure.
Okay, I'm just thinking maybe let's open up collab. Oops. Okay, today is mostly theoretical part. I'm gonna do the new workbook. Okay, so let's start with the first question. So chapter 12, exercise. Yeah. Okay, so the first question is, how would you describe TensorFlow in a short sentence? What are the main features? Can you name other popular deep learning libraries? So let's tackle the first. So yeah, so first of all, what is TensorFlow and why TensorFlow actually? The reason I say why TensorFlow, in a sense, we have a Keras, we have a NumPys, we have a Pandas. So from that perspective, what does the TensorFlow add? Anybody wants to take that? So my understanding is it's more of a machine learning framework, and it has all the libraries written in a different languages, and it's a portable. You can compile an ML program in one platform, and then you can run in another one. And most importantly, it works on the tensor. That is like a multiple. It's not a two-dimensional, but multi-dimensional arrays, and it process them in a parallel. So it's like more refined for a GPU. That's my understanding is. So anybody else want to chip in?
So how is that different from other frameworks?
So
It's the same, right?
yeah. So in a sense, I think it's a more elaborated framework from a perspective. So if we compare, like, let's say with the NumPy is mostly on the arrays. Like it's the high performance computation on the arrays, while TensorFlow is high performance computation on the tensors. So NumPy is more into CPUs, a TensorFlow for the GPU for parallel computation. In addition to that, I think the compatibility, like you can write a program on compile a program on in one language on one platform, but you can run in another platform, Linux versus Windows, or in-house versus cloud, that sort of stuff. My understanding is that. You can always correct me.
Yeah, I think these days PyTorch and TensorFlow are very similar in most ways. Whatever you can do in PyTorch, you can do in TensorFlow, and vice versa.
Correct.
And NumPy is it's just a array computation library, right? So yeah, I mean, it can handle tensors as well. It's not like it's only 2D arrays. It can handle tensors. But the only thing is you can't do like backprop gradient flowing stuff in NumPy.
Uh-huh.
You can't do that stuff. That yeah, which is what PyTorch and TensorFlow have.
Yeah, that's correct. So how this is going to be different than the Keras, the TensorFlow versus Keras, because Keras, what we have been doing is we have been adding all those layers, the dense layer or the activation layer or the optimizer, anything or everything. We have been doing all the Keras. So what does the TensorFlow add? Except I guess that the gradient descent method, the autograd, perhaps is a part of Akira's as well. So what advantage you have TensorFlow as compared to the Keras?
Yeah, I have not used either of these too much, but Keras is just a high level API on top of TensorFlow. So what might need 3 or 4 lines if you write in TensorFlow, you can just reduce it to 1 line in Keras. But underneath that Keras line is just TensorFlow code. So yeah, they have just simplified it and so that you can use it in 1 line. Similar to what FastAI does with PyTorch.
PyTorch.
So
Oh,
underlying that FastAI line is just a bunch of PyTorch code. But FastAI has done a lot of things to keep it keep it distinct from PyTorch as well. Yeah.
correct.
So it's not
Yeah.
a fair comparison, but yeah.
I thought the other way around for some reason. I thought the TensorFlow is written with the help of Akira's, but you're saying is other way around. It's more of a the
So
Keras is.
initially, TensorFlow and Keras were completely independent. So Keras was like a side project by this Francois Chollet in Google. He developed it by himself by just writing it on top of TensorFlow. And then you can switch TensorFlow for another framework called Theano, which was popular at that time.
Yeah.
So you can just choose what framework you want, but your Keras code will be the same. So it's just high level stuff where you can create easy deep learning networks. With few lines of code. Whereas in the backend you would have lots of TensorFlow or Theano code. But right now what they've done is they have made Keras the default API in TensorFlow.
Uh-huh.
So yeah, now you can say they are kind of ingrained in each other. Yeah.
Okay. And when you mention framework, so what does the framework, the TensorFlow versus PyTorch framework, we have a lot of talk. So one, I understand like that the autograd that is provided by these frameworks. What else? Like when we say framework, what do we usually add? That TensorFlow framework, Theano framework, or PyTorch framework? What's the definition? Do you have any idea in general?
I mean, yeah, it's called a deep learning framework because it gives you all the tools that you need for any deep learning problem, right? End to end, from setting up the actual network with the weights and layers and all of that, and then having a training loop, and then giving you the facility to uh, do the back propagation. Yeah, I mean, the framework it's called a framework in the sense that it gives you all the tools that you need
Mm-hmm.
for any kind of deep learning problem.
That's correct. Yeah. Okay.
Yeah, back propagation and weights biases, forward propagation, training loop, the optimization part mainly. Yeah, that as well.
Yeah.
The descent and yeah.
Okay. Cool. Yeah. That's a very good explanation. So what are the main features? That's exactly what we probably just discussed. And can you name other popular deep learning libraries? We already mentioned PyTorch or Keras we are mentioning. Anything else you want to mention for a question number one? Shall we go and then read out the answers?
Yes.
Okay, so let's try to go to the answers. I'll put it on the screen. So there will be a lot of at 2 and 4th, but let's try that this time around and see. So this is 12th. Okay. TensorFlow is an open source library for a numerical computation, particularly well suited and fine tuned for a large scale machine learning. Just first of all, you can see my screen, yeah?
Yes.
Okay. And its core is similar to Numpy. Let me get rid of this guy. Numpy, but also features GPU support for a distributed computation graph analysis, and optimization capability. So optimization capability will be with the portable graph format and allow you to train a TensorFlow model in one environment and run it in another. Yeah, that's what I was saying. And let's go back. I'm going to go back. GPU support, we said we find computational graph analysis. So I know it creates a graph, which perhaps was the bottleneck of a TensorFlow, wasn't it? That's why they went for a eager method in the 2.0. So any advantage you can think of computational graph analysis? Do we actually really do this graph analysis? Or it's just a bone? It's rather than having advantages. It wasn't giving much of the much of the value. Any opinion?
I think if you do that, it allows you to like to not do computations that are not necessary. So like you can optimize it with graphs a little bit better if you do. I think, I'm not sure. That's what I've heard. But yeah.
So in a sense, I think the advantage which I would say is the when we do the analysis. So basically the running part, it's going to do itself. It's going to find out the best optimized method and it's going to run. The analysis would be mostly like a debugging or how it's computing the values. I'm not sure, like I haven't seen him giving much example except drawing that graph and then just saying, okay, it will run most optimal way. Okay. So, and optimization capability with the portable graph format that allow you to train a TensorFlow model in one environment and run it to another. Okay. And optimization API based on reverse mode autodiff. So this is autodiff would be your autograd, I guess. We call it as a autodiff here. Is that correct?
Yeah, I think so.
Yeah. And several powerful APIs such as TF Keras, TF Data, TF Image, TF Signal, and more. Okay, so in a sense, these are the APIs we were discussing. What are the other libraries? So Keras, TF Data, TF Image, TF Signal, and more. Other popular deep learning libraries included PyTorch, yeah, MXNet, Microsoft Cognitive Toolkits. I heard about this. Never used it, but I heard about this. Theano, I think it's kind of Theano, Cafe, and these are before PyTorch, I guess. And a chainer, never heard before. So I think most of the time, which I heard is either PyTorch or a TensorFlow. And interestingly, TensorFlow is more of production, the production ready toolkit, and then PyTorch is more into a research guys. So while PyTorch is quite, you hear a lot about it, but when you look on from a production deployment perspective, it's more of a TensorFlow. Have you seen that similar, Maria or Gautam? What's your view on it?
No, I'm unfamiliar with most of them actually. You know, PyTorch is the only one I've kind of PyTorch. Yeah.
Yeah, I generally agree with you. Yeah, from what I've heard, TensorFlow is still more popular, and TensorFlow skills are also more in demand in the industry.
Hmm.
Yeah. And I'm disappointed that he has not mentioned FastAI, but he has mentioned Microsoft Cognitive Toolkit and stuff.
Yeah, well, that's the interesting part. Like, would the fast AI would sit in the framework, or would that be the fast AI will be sitting more towards the Keras, which is just a top layer of, like, which is more of a user interface?
I think FastAI, Jeremy has written so much things that is independent from PyTorch as well. So I
Mhm.
think it has earned the right to be called as a deep learning library. He has written a
Oh,
lot of stuff
ah,
that's independent of PyTorch. Yeah.
yeah. All right. Yeah, yeah, yeah. You mean, so when we say Microsoft Cognitive Toolkit, do you have any idea? Like, have they written from scratch? Like, have a
Yeah.
compiler, or
It's I
they're
think it's called CNTK. It does not even exist anymore. Even Microsoft does not use it, I think.
all right?
Yeah.
The book probably is older than, yeah.
Yeah, I think he used the answers from the previous edition, probably.
Okay. Yeah, yeah. Okay, so take a pinch of salt. We are
Even
aware.
Chainer does not exist now. So they
Yeah,
have
yeah.
moved to PyTorch.
Yeah, I never heard. So maybe Chainer can be replaced with the fast A. All right, let's go to the next question. I'm gonna scroll up back to our chapter 12. Okay, so next question is TensorFlow uh, is TensorFlow a drop-in replacement for a NumPy? What are the main differences between the two?
I think the previous question already mentioned this, right? Talked about this.
Hmm,
So GPU and GPU support and the auto grad. Yeah,
correct.
I think these two are the main.
Autodiff. Yeah.
Yeah.
In addition to that, the TensorFlow, as you mentioned, it's more to do with the writing the machine learning those layers, and then doing all that all sort of a programming. With NumPy, I don't think we can do like writing those layers, or and then start doing the each and everything, all the calculations. We are doing the layers, convolutional neural networks. We have the activations or optimizers. If we try to do from scratch, let's say, can we do that in a NumPy?
Yeah, I mean, you could create if you wanted. Yeah, if you really wanted, you could create layers and activations and optimizations in NumPy.
In a NumPy. Mhm.
Yeah, yeah,
So that wouldn't be
yeah. I'm not exactly sure how AutoGrad is written, but yeah, yeah. Anyway, TensorFlow also had to be developed from scratch, right? It's not like so. Yeah, maybe you
yeah.
could do it in NumPy.
Yeah, so another question I have in for a TensorFlow. Is it TensorFlow written in C, C++, or is it written in Python?
Yeah, it's C++. I think yeah, C++. Because
So
C++,
why?
it's that's how you connect with the GPU
Yeah.
and yeah, all of that stuff. You
So
would need to write it in C++.
so in a sense, I got confused. You remember initially FastAI was written in a TensorFlow, and then he moved on to PyTorch because he goes that the Python was clunky. That's why he moved to PyTorch.
Yeah.
Any insight? Why did Jeremy move from TensorFlow to a PyTorch. I thought it was because of the Python, but in a PyTorch there is a Python as well. So that's the confusion I have.
I mean, there would be both, right? TensorFlow, the core of TensorFlow might be in C++, but still some of the code would be in Python as well. It's not
Yeah.
like the whole thing is. For example, the language Python itself, like some of it is written in C, and then rest of it is written in Python itself. Yeah, so it's similar to that. So TensorFlow, some of it is written in C++, and then you have some parts written in Python.
Python.
And so there is another language called Julia. So
Yeah.
so in Julia, everything is Julia itself. So they have their own deep learning frameworks, and it's all written in Julia itself. So the advantage is that you don't have to everything. All the errors will be much more easier to debug. Whereas in TensorFlow, the error might go down to the C++ layer. So things get tricky and all of that. So, but whereas if it's fully written in the same language, it's much more easier to work with.
So we are saying TensorFlow is kind of a mix of two, like C, C++, and a part in Python, like maybe higher level on a Python, I guess.
Yeah. I'm not sure if C is there, but C++ is definitely there.
Okay.
Yeah.
Okay. All right. Let's read answer to this. Let's go down the chapter 12. Okay. So although TensorFlow offers most of the functionality provided by the Numpy, it is not a drop-in replacement for a few reasons. First, the name of the functions are not always the same. For example, tf.reduce_sum versus num_sum np.sum. Oh yeah. So one of the difference was like it's a 32-bit byte float, while the numpy is 64. I think it's 64, and then that's the reason like your sum may not be exactly the same every time you run the same program because of the floating point precision. So that's the one point he's trying to. That's why it's a reduced sum rather than a direct sum. And does this make sense?
Can you repeat that?
So in the TensorFlow, the numbers are a 32-bit floating numbers. And the NumPy, they are a 64-bit floating point numbers. So when we do the sum, because they are 64-bit, 64-bit floating numbers, so when they add up, you don't lose any information out of it. So when you do time and again, you'll get a sum exactly the same. However, the reason it is a reduced sum, reduced underscore sum, because it's a 32-bit floating point numbers, which TensorFlow uses. And the reason it uses 32-bit floating point number is to expedite the performance. However, you might lose a tiny bit of a precision. So that's why it's a reduced sum rather than exactly the sum. Yeah.
Okay.
Okay.
But you can
so,
change the default type, right? You can make it 64.
You can, I think you need to define separately. Yes. So even if you define, let's say if you define a number, you try to add them, it doesn't do the casting for you. You need to do cast explicitly. So I think he covered that initially somewhere in the chapter. He mentioned that.
But I think the word reduce probably has some other meaning, because I have read somewhere that the word reduce is taken from the language of functional programming. So in functional programming, the word reduce has some other meaning, and that was inherited to this.
From there, okay, Bob didn't have any clue.
Yeah, I can search about
Yeah,
it.
have a look. Yeah, have a look. Yeah, that would be interesting to know. Yeah. Okay, so second, some functions do not behave in exactly the same way. For example, TF transpose creates a transposed copy of the tensor, while numpy's T attribute creates a transposed view without actually copying any data. Okay, yeah, he mentioned that when you do the tf.transport, it's going to create a new object for you. But in a numpy, when you do a number.t, it's just a view that is just pointed to the same object. So if you make a modification as a transposed number variable, you're going to get that reflected into a main variable as well. And last, NumPy arrays are mutable, while TensorFlow tensors are not. But you can use TF variables if you need mutable objects. So what does it mean? NumPy arrays are mutable. So mutable means like they can be overwritten. Is that what mutable means? Yeah. So you can they are variables, so you can write on them. While TensorFlow tensors are not. Okay, but you can use TF variables if you need mutable object. Okay, but most of the time we would need a mutable in a sense when we are adding, subtracting, multiplying. So okay, maybe perhaps when you do that multiplication of the matrix or addition, it creates a new object. Yeah, and this is where he said, like when it transpose, rather than keep referring to the same location, is going to keep creating new objects. That brings another issue that you're going to start using a lot more memory. However, because we are using a 32-bit precision, float precision, so probably it's saving a memory there, and then perhaps it's probably keep on regularizing it, not regularizing, but the garbage collection, perhaps somewhere it will be doing it to release the memory of each object as we go along. All right, anything else you want to discuss on this?
Yeah, another point is in deep learning, you don't really need too much precision, right? Because you're not doing some engineering calculation or anything. It's just yeah.
Correct.
And most of the time we actually reduce the precision to get regularizing effect, which is called I forgot what it's called.
Yeah.
Quantization, I think. Yeah, quantization. You can reduce the precision to not only reduce the overall size of your network, you can also increase the performance. Yeah.
Quantization. Okay. All right. Cool.
And regarding the last sentence, I think yeah, and the weights and biases of a neural network have to be modified all the time, right? So I believe they are TF dot variable objects, because we need mutable objects.
Okay. Yeah. Makes sense. Yeah. So by default, they are immutable. But if you want to create object which need to be updated time and again, as you said, weights and biases, they need to be TF variables. And I'm not sure why they have taken a decision that they are going to be immutable. The objects are immutable, not to be updated by default.
It gives some efficiencies. Like for example, tuple is immutable and list is mutable. So when you when you access elements from a tuple, it's much faster as opposed to a list. So maybe something like that. Yeah.
So if the objects are immutable, then
if they are immutable, it makes things more efficient, like indexing and querying, accessing, and all.
Yeah, you're right actually. And if you look from the general perspective, AWS S3 object storage or Google Cloud Storage, they all are immutable. So I think probably you're right from an access perspective. It's probably a faster to do the immutable. Perhaps in the back end, how they make it as immutable requires a lot of processing. Okay, let's go to the next question. So we're going back. Question here. Okay, question number 3. Do you get some same result with the TF range and TF constant NP range? So let's do this here. So import TF. So he says TF dot range 10. So it's going to give us 10 numbers. Okay, NumPy array and TF constant.
So this is 1 hour. Yeah.
Okay. Shape 10 data type. So see here, it's 64 because it's an NP array. Here we did just a tensor, which is 32 bits, and then rest is same. Yeah. Yeah, that's the only difference. You get the same result. Only the data type is different. So TensorFlow 10 numbers are floating point precision 32, and then in NumPy array we have a 64. Yeah, so let's go back and then check what he says. I think he's gonna say same thing, but oops. Oh, answer, sorry. Good. And here, both TF range 10 and TF constant NP range 10 returns a one-dimensional tensor containing integer 0 to 9. Fine. However, the former uses a 32-bit integer while the later uses a 64-bit integers. Indeed, TensorFlow defaults to a 32 bits while NumPy default to 64-bit. Yeah. Okay, so that reaffirmed our understanding that difference between NumPy and TensorFlow. So that's good to do. Yeah. Okay. Anything you want to add, or you want me to move on to the next question? Okay. Let's move on to the next one, sir. Can you name 6 other data structures available in TensorFlow beyond regular tensors? Okay. So we keep on saying it gives us the tensors. What other data structures TensorFlow gives? TensorFlow data structure. What does this data structures means? Does it mean by variables, or I'm not sure. Regular
It's
tensor.
just the type of like a container for data, right? So I think graph might be one of the, yeah.
What do you
One
say?
of the, so it's just the container of the data. I mean, what type of data container do you have? I mean, that's what a data structure is, right?
Okay, so one he gave us tensor. Okay.
Yeah, I mean, I'm not. This just shows my unfamiliarity with TensorFlow. I think graph might be one.
Graph.
Graph.
Oh, graph. Sorry.
The yeah,
So that you're saying the graph holds it's a data structure.
yeah,
Okay.
it's a data structure. Yeah.
Okay. I have no clue with the even with the question. I still don't know anything else you want to add, or shall we jump into answer? Yeah. Go ahead, Maria.
I don't know these things, but I think the answer is in like figure 12.1. So they there point out some special data structures. I mean, I wouldn't have guessed a lot of them, but some of them, I guess. But I,
So-
like you, Dinesh, don't understand what they mean by data structures either.
So you mentioned 12.
12.1.
12.1. Okay. Let's see. Come on. I need to find a better way of searching. 12.2. Oh, this. Oh, 12.1. Okay. Yeah. Okay. So these are the TensorFlow Python API.
Yeah, so on the right column, the second one. Yeah, there you go.
This one? Okay.
Yeah, the one that you're pointing at. Yeah.
Yeah. Okay. I remember sparse. I remember ragged. Yeah. So you have like a sparse metrics. You want to store it. That was special, I think. Yeah. Ragdo is there. Nest, I don't know. Lookup, I have to do. Sets, I think we read that. Yeah. Anyway, so and graph. When you say graph, Gautam, did you mean any of them?
No, I think I was wrong.
Okay. Okay. So we're saying we have a tensor, we have a ragged, we have a sparse. I'm gonna write which I kind of have sense. I think I somewhere read sets, but other than that, the new thing would be lookup. Need to find out what the lookups are. And nest. I think nest.
Is the lookup not like the lookup tables?
Yeah, well,
Yeah, but then I don't know.
in a sense, in what context, Nest, I can think of, there is a one place he mentioned that list of a list, a tensor of list of a list, something like that. But I think, but that goes into, I think, ragged tensor. When you have,
yeah.
when you have,
Yeah, go on.
yeah, when you have a list of tensors, and then that the list, which is list of, is like a different size, that goes into ragged. Is that correct?
Yep.
Yeah.
When the dimensions don't match. Yeah, exactly.
Yeah. And the sparse would be when you have a lot more, like lots of zeros. So instead of storing all of them, it stores only the values where the values are stored. So that's fine. Strings.
You mean the position where they're not zero?
Yeah. So I'm like it. Yeah, exactly. So I think there are a couple of methods the way they store these sparse metrics. So instead of storing all the values, they have a very clever way of storing only where the value lies. So it stores the position where the value lies, and it can be calculated two different ways. One is when you can go along the row, like you start from first element of a row and then you walk along the row, and then once the row finishes, you come back to the second row and you go like a snake, you know. And Rachel, I think one of the NLP classes initially, Rachel's class, she showed it. And another method is, I think, you walk along the columns. So all in all, sparse matrix, I think, stores the location of the values as, or it kind of like decode the location so that it doesn't have to store the value, all the zeros. So that's in general my understanding. Okay, and 7 is strings. Strings are strings, so dealing with the names. Yeah. Okay, so thanks for that, Maria. Yeah, this was very helpful. Let's go back to, let's read it. Read the answer. Okay. 12.
Dinesh, can you, is it possible for you to open 2 windows of the PDF so that you can?
No, this is the problem. So what's I tried. I'm more than welcome to. Oh, actually, you know what?
You can
No.
open one in your browser, right? One instance in your browser, I think.
Okay, let's try.
Browsers do support PDFs.
Okay, so actually, this is not a PDF. This is a.
Okay, got it. Yeah. Okay.
I have a
Yeah.
PDF, but PDF doesn't have the exercises.
Okay.
And what I try to do is I try to take I didn't do much research, but I try to take a copy of this to a different location and try to open it. But it's the books is clever to have a pointer rather than another copy. So
Okay.
sorry about that.
Yeah, no issues.
Okay, so okay, beyond regular tensors, TensorFlow offers several other data structures, including sparse tensors, tensor arrays. What is the tensor arrays? Tensor of arrays, okay. Rag tensors, queues, strings, string tensors, and sets. So this thing came new.
Are tensor arrays not the same as tensors?
That's what I thought. Sparse tensors, tensor arrays, and queues.
But maybe the tensor arrays is like a list of tensors, like that are not ragged.
It's probably, yeah, yeah. List of arrays. List of lists, but they are not ragged. Yeah, potentially.
I'm not sure, but yeah.
Or perhaps just a list.
Hmm.
No.
Yeah.
Okay, TensorFlow provides special function. Okay, last two, the queues and string tensors and sets. The last two are actually represented as a regular tensor, but TensorFlow provides a special function to manipulate them. So TF strings and TF sets. Okay, but yeah, so in a sense, the strings and the sets kind of like is the tensors, but the queues, ragged makes sense, sparse makes sense, tensor arrays. Let me see what is, if we can find something quickly. A tensor is
Yeah, it's the link tf.tensor array. Yeah, down. The third link.
third link. This one.
No. Below that, the one below that. Yeah.
This one. Okay.
Yeah.
Okay. So let's read the tensor arrays, data type, size, dynamic size, clear. Doesn't give you much.
I think it's similar to, since it says dynamic size, it's similar in that sense to the rag tensor, since that is also the size is not a constant.
Doesn't give you any definition on the functions given, but I was just looking if can. Okay, sorry about the scrolling. I'll go slow this time. Yeah, all the functions, arrays, methods. Just stop. The output of this function should be used. Yeah, okay. So this is all the functions. Let me go up. So you're saying dynamic size. Oh, right. Sorry about that. So you're saying dynamic size is none. That means it can't be contracted. It can't be go like ragged. Ragged would be a dynamic size is equal to true. Is that what you're saying?
Yeah, I don't know the exact difference, but
Let's see.
yeah, that aspect would be the same.
I see. Yeah, so here the definition is given very clearly. You can read through it and you can make sense of it. But over there, he's just not giving us much.
Probably not that important to know all of this. Yeah.
I guess you're right. Yeah, just move on. If we don't know, we don't know. Okay, so let's go to question number 5 then. Okay, so let me go up. Come on. Okay. Okay, so the next question is, a custom loss function can be defined by writing a function or by subclassing the keras.losses.loss class. When would you use each option? So custom loss function, I think it's usually if you inherit from the loss class, then you'll have access to all the methods available in a loss class. That's when you will be subclassing it. And to use it, use case, most of the time you should be doing this, I guess. And if you just define by writing just a function would be, it's accessible just internally, I guess. Okay, anything else you guys want to add? When it should be using either of the option? Shall I go to the answer then? Okay, let's go and read out the answer. Question number 12. Okay, when you want to define a custom loss function, in general, you can just implement it as a regular Python function. However, if your custom loss function must support some hyperparameter or any other state, then you should subclass the keras.losses.loss class and implemented the dunder init and call methods. If you want the loss function's hyperparameters to be saved along with the model, then you must also implement a getConfig function, getConfig method. So all in all, we are looking at if your custom loss function must support some hyperparameters. So hyperparameter means I remember there was one where I think it was Huber loss, where we were passing on the threshold. So if you want to give some value, externally specified values to the loss function, then you need to subclass it. Otherwise, if it just simple, let's say you're defining your MSC, you can define through the custom loss function. I think just a simple function, regular Python function. But when you're defining with some hyperparameters, then utilize this. You with me? Make sense?
Yep.
Yep.
Okay, so let's move on to the next one. Let's go back to question number 12. Next week I'll make sure I have 2 copies of this so that we can do side by side. There must be some solution. I'll find out. Okay, so next question is, similarly, a custom metric can be defined in a function or a subclass of keras.metric.metric. When would you use each option? Okay, so similarly, a custom metric can be defined in a function or a subclass of a metric. When would you use each option? Okay, any view? Or I should just read the answer. Okay, let me go and read the answer. Number 6. Much like the custom loss functions, most metric can be defined as a regular Python functions. But if you want your custom metric to support some hyperparameters or any other state, then you should subclass the keras.metric.metric class. Moreover, if computing the metric over a whole epoch is not equivalent to computing the mean metric over all batches in that epoch, as for the precision and recall metrics, then you should subclass the keras.metrics.metric class and implement the dunder init, update state, and result method to keep track of a running metric during each epoch. You should also implement the reset state method unless all it needs to do is reset all variables to 0, 0. If you want the state to be saved along with the model, then you should implement the getConfig method as well. So I remember it. You remember he gave an example that I think it was a precision. He was looking for a precision that in each, because the metric we calculate on each batch. However, we cannot take a mean of all the batches and we say, oh, this is the final metric. You have to calculate the metric for each batch, but you keep on going, adding them as you go along the batch, which it calls a streaming metric. Do you remember anything?
Yep.
Yeah. So, and that's exactly what he's saying, I think here, that if you have like a, the precision and recall metrics. So if you're doing that, calculating it, then you need to update the state as you pass through the stage, and then you keep on adding those values to those precisions on every batch stage. And perhaps if you want to reset to a 0 at some stage where you think, oh, I need to reset them, and then maybe perhaps after a few epochs, I don't know, whatever stage, so you need to get this method as well, then you'll use it. And obviously, if we have to save a model with the hyperparameters within the metric, if we want to save it, then we need to use this function as well when we're rewriting it. Am I making sense? Is it good? Any question on this? Any viewpoint on this? So this was very interesting. Okay, I'm going to move on then if there is no question.
So this streaming thing comes into play, I think, only when your batch sizes might become different. For example, if the first batch has 5 and the
Yeah.
second batch has 6, then you should not just take a simple average because they are having different number of examples. So you would take a weighted average or a, yeah, if you do update state, then you get that running average thing.
That's the legitimate case. However, most of the time you're going to have the batch size is going to be same.
Yeah, but sometimes the last batch
Last batch,
might,
yeah,
yeah,
yeah.
yeah,
But at the same time, I think the example he was giving is if you have a same batch and if you have like, let's say, he was saying 5 out of 4 are the correct one, true positive, and then in the next time you have a 0. So now you have a 10 cases, your true cases are only 4, and then you can't take I think a mean, because that, okay, let me open an example here, so that would be good if I can find that's the answer. It was somewhere in the chapter he discussed, he gave a very elaborated answer. Let me find out and then we can walk through variables, custom loss function, and I think
okay, I think I got what you're saying. Yeah, it's page 389.
page, I have different, okay, so you got it on your side, yeah.
Yeah,
Yeah, here. Yeah, I think this is where he explained in detail. Yeah, so 80% precision, 40% precision, and do you want me to go through it, or
I got it, but you can go through it if you want. Yeah.
let's go one quickly once as a group. For each batch during a training, Keras will compute this metric and keep track of its mean since the beginning of the epoch. Most of the time, this is exactly what you want, but not always. Consider a binary classifier precision. For example, as we saw in chapter 3, precision is the number of a true positive divided by the number of a positive predictions, including both true positive and a false positive. Suppose the model made a 5 positive prediction in the first batch, 4 of which were the correct, that is 80% precision. So 5 positive prediction, however, we have 80% precision. Why we have 80% precision? Because true positive by so one false positive in there. So that, but we are looking for only true positive. So 80% precision. Then suppose the model made a 3 positive prediction in the second batch, but they were all incorrect. That is a 0% precision of the second batch. If you just compute the mean of these 2 precision, you'll get a 40%. So we have 5 plus 5, 10, and then we have a 4 right of it, and then it's a 40%. But wait, second, that's not the model's precision over all these batches. So remember, we have sorry, let me complete this and then I'll come back. Indeed, there were a total of 4 true positive out of the 8 positive predictions. Yeah. So the overall precision is 50%, not the 40%, because we have 4 we made here, 5 we made in a first case, 3 we made in a second case. So we have 8, and 4 out of 8 are the yeah, 4 out of the 8. 8 is the precision. 8 out of 4 out of the 8 is the 50%, not the 40%. So that's what is the example he has given. Am I making sense here, or is it too confusing?
I
No,
got it.
makes sense. Yeah.
Okay, cool. We are 3 of us, so it makes sense. Okay, so that was the example he has given. So let's move on to the next question. 12 here. Okay, so 6th, 7th. Okay, is the answer, is this, these are the answers, sorry. Yeah. Okay. When should you create a custom layer versus the custom model? Okay. Custom layer versus custom model. So what's the difference between a custom layer versus custom model, first of all?
What exactly is a custom model? Aren't all models custom? Like you're making something on your own, right?
Yeah. The custom model would be, so here is a custom model.
But could you not like ask for a regular model like CNN or yeah, like a ResNet or a VGG? Would that not, that wouldn't be a custom one, right?
Yeah, that's exactly what he had. That what he was saying is in this case you have the residual network. I think when you have a network and a auxiliary network on the side as well, I guess. So you have gradient descent going in main model, but you have auxiliary network on the side. So you have that like two models going. You may or may not want to use the auxiliary model within the main model, or you can add the loss of it.
So this is the, I mean, this is where PyTorch is slightly easier to comprehend. In PyTorch, everything is a module. There is no distinction between a layer or a model. Everything is a module, so it's easier to think about stuff.
Mm.
Yeah, in TensorFlow you have model object and a separate layer object.
Yeah, yeah. And so the layer goes in the model. So what we're doing is just we're building different layers and adding, and I think layers are kind of the example he gave here. When you have, it's let's say, the block. So we were saying here, let's say if you want to repeat this block many times, so you create a layer of it and then start using it. That's the custom model, a custom layer, I guess. Let's read the answer. See what he says.
So if you have a model object, you can't use it inside another model, right? You have to re-implement it as a layer, and only then you can use it inside another model. Is that what you're saying?
So so model should be just a one complete
Yeah, I got it.
block,
Yeah.
which, you know what I mean?
Mhm.
You can't. Can you use a model within a model? I don't think so.
Yeah. No.
Yeah. Okay, so seventh question. You should distinguish the internal components of your model, that is layers or a reusable blocks of layers, from the model itself, the object you will train. The former should subclass keras.class.layer class, while the later should subclass the model. Not really. I think I understood the part, the layers. Why would you need a layer? So like, as he said, when you want to make reusable blocks, so you start creating more layers. So that makes sense. And then obviously, once you subclass it, it makes easier for you to access any method defined, and then it's always a good practice, blah, blah, blah. However, custom models, he didn't explain much here either. But as Maria said, I think when you have a residual network, or you're defining some network, or perhaps let's say, the ResNet or VGG, or you want to create that kind of a network itself, that would be a model within itself, wouldn't it?
Yeah. But if you are making a big network, that takes in VGG and then adds a layer on top of that,
Mm.
then your VGG should be a layer. I think that's what this answer says. So then your VGG becomes just an internal component of your model, right? So then VGG will become, as a whole, will become a layer,
Yeah.
and then whatever thing you're adding on top of that is another layer, and the whole thing is a model. So model is like a collection of layers or a sequence of
Correct.
layers.
That's correct.
Yeah.
And
So in,
correct.
yeah.
That's correct. And then, for example, I was looking into that NLP Quora question answers through the Siamese network. So Siamese network, there is no pre-built API or anything. All you do is you add LSTM and you add the tensioner and a bash norm and everything, and you create a network. But you're using a LSTM in it as a layer, or you can use anything GRU or whatever. So that model which you are building is your custom model. Isn't that correct?
Yeah.
Yeah. Okay, let's move on. At least we should go up to question number 10, so that we show some progress. Okay, so I'm gonna just hurry up a bit. We have 15 minutes left. So question number 8. Question number 8. What are some use cases that requires writing your own custom training loop? Okay, so custom training loops. So what are these loops now? Okay, should we go maybe look in here? Custom layers, models, internals. Here, custom loops. In some rare cases, the fit method may not be flexible enough for what we need to do. For example, the wide and deep paper we discussed in chapter 10 uses 2 different optimizers, one for the wide path and another for the deep path. Oh yeah, I think if we can go here, I think he's talking about the one which wide and deep. I think it was ResNet, which not ResNet, but auxiliary net. No. Yes, I think something similar. So you have these, and then coming here. Let me see. Oh, this is the one. This is the one I think he's talking about, that you have one path going in here. So this is auxiliary, and one is going in here. So you have kind of a 2 loops for the network. Let's go back. So I think this is what he's referring to. Go back to the custom loops. Here. So wide and deep, we discussed in chapter 10 to use 2 different optimizers, one for a wide path and another for the deep path. Since the fit method only used the one optimizer, the one that we specify when compiling the model, implement this paper requires writing your own custom loop. Okay, and you may also like to write a custom training loops simply to feel more confident they do precisely what you intend them to do. Perhaps you are unsure about some details of the fit method. It can sometimes feel safer to make everything explicit. However, remember that writing a custom training loop make your code longer, more error prone, and harder to maintain, obviously. Yeah, but then I think this is the legitimate case, like if you have wide and deeper network. So I'm going to just read answer as well. Probably he has the same answer down below. And feel free to interrupt if you want to add something. Okay, writing your own custom training loop is fairly advanced, so you should only do it if you really need to. Keras provides several tools to customize training without having to write a custom training loop. Callbacks, custom regularizer, custom constraint, custom losses, and so on. You should use these instead of writing a custom training loop whenever possible. Writing a custom training loop is more error prone and it will be harder to reuse the custom code you write. However, in some cases, writing a custom training loop is necessary. For example, if you want to use a different optimizer for different parts of your network, like in a wide and a deep paper, a custom training loop can also be useful when debugging or when trying to understand exactly how training works. So I think that's the gist of the question is trying to say. When you want to use a different optimizer for a different part of your network, then you write the custom loop. At least we are far away from that. Okay. Anything else you want to add to this question? Question number 8 makes sense or?
Yeah, makes sense.
Okay. Let's move on to the next question. Question number 9. Can custom keras component contains arbitrary Python code or must they be converted to TF functions? Can a custom keras components contain arbitrary Python code or must they be converted to TF functions? Anybody remembers what was TF functions? Let's review quickly TF functions. Oh, this is TF functions. Is this autograph and tracing TF function? Most of the time, converting a Python function that perform a TensorFlow operation into a TF function is trivial. Decorate it with the TF function or let the keras take care of it for you. However, there are few rules to respect. If you call any external library, including Numpy or even the standard library, this call will run only during tracing. It will not be a part of the graph. Indeed, a TensorFlow graph can only include TensorFlow constructs, tensors, operations, variables, dataset, and so on. So make sure you use tf.reduceSum instead of an np sum, which we discussed, tf_sort instead of a built-in sorted function, and so on. Unless you really want to code to run to, unless you really want the code to run only during tracing. This has a few additional implications. If you define TF function fx that just returns np random.rand, a random number will only be generated when the function is traced. So ftf.constant.2 dot and tf constant 3 dot will return the same random number, but tf constant 2 dot and 3 dot will return a different one. If you replace np random dot rand with tf random uniform, then a new random number will be generated upon every call, since the operation will be part of the graph. I'm going to go back, try to interpret what the tf function is. So tf function is kind of like just have a decorator on the normal Python function. That's my understanding. Is that correct?
Yeah, and I think it makes the graph associated with that function,
Yeah.
so that it can be optimized and all during runtime.
So TF function, yeah. So as you said, it will make a TensorFlow graph. So that get included into the graph optimization as such. So TensorFlow will, I guess, then will take over to create a graph and then find the most optimized path within your function to execute it. So it will optimize your function automatically if you include decorator TF function on your Python code. If you don't do it, then it's going to do whatever you want to do it but that may or may not be the most optimized way. That's my understanding.
So any ideas like where would you use a TF function that you wrote inside a neural net? I mean, yeah, any examples for that?
I guess the TF function would be your, like when you're writing your custom functions, for example, you're writing your custom metric function or custom loss function. That would be the TF function, I guess. Whatever Python functions you are writing, custom function you're writing, be it for the metric or be it for the loss, when you decorate it with the TF function, that they becomes a TF function.
But if you inherit the keras.losses, it would be automatically a TF function, right?
I am not sure, because that's not a decorator. That probably inheriting the property of a keras only. That wouldn't make it as a TensorFlow function.
Okay.
Because it's gonna inherit the class itself, and it's going to do whatever the class is doing. However,
yeah, but what if the class is making a TF function internally? We don't know that, right?
Yeah, that's a good question though. Yeah.
Because I have never seen like TF functions, the decorators being used.
My take on this chapter is, this is one of those chapters that you take with a pinch of salt. You say, yeah, you can do it, but probably we're far away from doing it, because everything he's saying is like, he's saying, oh, don't do it, and he has just mentioned bits and pieces here and there. I never used it. I just did use whatever he mentioned it. That's pretty much it. Okay, let's read answer. Anything else you want to add, Maria, of the same question?
No, good, sir.
Okay. Custom keras components should be convertible to TF functions, which means they should stick to TF operations as much as possible and respect all the rules listed in TF function rules. If you absolutely need to include arbitrary Python code in a custom component, you can either wrap it in a TF.py underscore function operations, but this will reduce performance and limit your model's portability. Oh, maybe portability is another question, or another advantage, I guess. Or set dynamic true when creating a custom layer or a model, or set run eagerly true when calling the model compile method. Okay, I'm gonna read this part again. If you absolutely need to include arbitrary Python code in a custom component, you can either wrap it in a tf.py underscore function operation, but this will reduce performance and limit your model's portability. Or set dynamic equal to true when creating the custom layer or model, or set run eagerly true when calling the model compile method. Okay, so it's more or less, he's just giving us like, what should you do if you try to create an arbitrary Python code rather than decorating it with a TF function.
So I think if you create a custom layer or a custom loss, custom metric, they will be automatically converted to TF functions. That's what it looks like from this answer. Whereas if you use any standard Python functions like np.random or something like that, that would impede, it would come in the way of conversion to TF functions. So that's why he's saying stick only to TF operations.
Yeah, and I think I refer back to your earlier question when you said, oh, what if we inherit a class So I think if you inherit from the TF class, so I think then you should be fine. It's only the arbitrary Python code where you are not inheriting, like say Huber loss. He has given example, and we are not inheriting from any class like Keras.losses.loss class, and but we still want to use it. So in those cases, he is suggesting us do these things if you still want to use that without
No,
inheriting.
but even inside a inherited keras component, you should not use other Python functions. That's what the first sentence says. You should stick only to TF operations. So that's why np.random has an equivalent tf.random or something, which he showed in the earlier paragraph.
Yeah. Okay, so so you're saying even if you write the arbitrary Python code, you should use the TF operations rather than just yes. I know what you mean. Like
Yeah.
rather than using a sum, use the reduced sum.
Yeah.
All right, let's do the last question, question number 10, and then we should be done for today. Okay, we know the answer. Please refer to the TF function rules for the list of rules to respect when creating a TS function. So I guess he's asking what are the rules. Okay, here. So question number 10, what are the main rules to respect if you want function to be convertible to the TF functions? So I guess we got to read a couple of things you already said. That when we are doing those operations, we need to, like these guys, like reduce sum rather than a sum, TF sort instead of built-in sorted function, so on and so forth. And then I think rest they have listed here. So you can call other Python function or TF function, but they should follow the same rules as TensorFlow will capture their operation in the compilation graph. So I think this is the important part, as you mentioned before. So whatever Python code you want to write, you want TensorFlow to include your code in a computational graph. And to include that into a computational graph, I think you need to stick with the TF operations, as you were saying before, to be decorated. And then he says, note these other functions do not need to be decorated with the TF function. So if you have done the, I think the rules are given here. All the rules are given here. So we can read through it. I'm just gonna leave it. I'll read it after the class. Okay, so I think we are on time. It's 6:30.
Yeah, I wonder why we don't hear about these things in PyTorch, like these rules and TF function, equivalents to TF function and stuff. Never heard about these things in PyTorch.
I don't have a much experience in PyTorch either, so I don't know. To be very honest with you, I found PyTorch is slightly different when I look at even like the any collab notebook. It's more of like functionally written, like it's all of them are functions written, build model, create model, and then call. Here we kind of doing the layers. The layers we do, we don't do layers over there. I haven't seen those layers over there. So for me, it's quite a different way of writing models, PyTorch versus TensorFlow. But I have to confess, I found it a little bit easier to understand the TensorFlow, or maybe because I never gone through quite a detailed PyTorch. I looked just at Jeremy's work and then few notebooks. Anyway, so that's pretty much it. Anything else you guys want to discuss, or should we break? All right then. Thank you both. Thank you for your time, and It was fun. We'll meet next week, same time, and then we will go through. Let me see what we're gonna go through. I think just a couple of questions left, but next week we will do much exercise. So question number 10, 11. Okay, so only one theoretical question, but then exercise 12 and 13, we're gonna use the hands-on notebook. So we'll walk through a notebook next week, question number 11, 12, and 13. And if we have a time, we'll move on to chapter 13. Otherwise, we spend time on 12 and 13 on the code side. Okay, doc, that's great. Thanks very much. Thanks for your time.
Okay, thank you. Bye.